Okay, so first, I guess, thanks to the organizers for inviting me. Thanks. It's really fun to be here. So I'll talk about sort of ideal lattices and Ring-LWE, but more from a real cryptographic perspective. And what this means is that, I don't know, sort of, at least my perspective is, yeah, okay, ideal lattices, I guess they're nice, but as a cryptographers, we're not really supposed to care about the beautiful structure or anything like that. They have to have some purpose, right? So the fact that we're using these kind of means that they are, in some sense, kind of the best tool for whatever job that we have. And sort of this talk will be about motivating why these ideal lattices that we've been studying is sort of the best, or at least we think is the right tool, or they're at least the right formulation of what we want to build our schemes upon. Okay, so so let me just, I guess, recap. The beginning will be pretty simple, given all the, because I wasn't sure what was going to be covered the first 2 days, so perhaps it'll be quite repetitive. So first we have, so let me just define cyclic lattices. Okay, we know this. So we know that a set L is a cyclic lattice if, just a definition, so it has this first property that for all elements in L, their sum is in L. So I'm going to use 4-dimensional lattices for every example in this talk because it's quite convenient. The negation is in L, so okay, these two properties say that it's a discrete group, subgroup. Okay, and then you have that every cyclic shift of an element is also in L. So, negative 1, 2, 3, 4, okay, is in L. Okay, anyway, it doesn't matter. So if this is in L, then the rotation is in L as well. Okay, and so of course cyclic lattices, you should think of them mathematically as ideals in Zx mod x to the n minus 1. And so, just doing the same thing before, it's just all about a notation, right? So instead of thinking of things as vectors, just think of them as polynomials where the coefficients are those vector elements, okay? So instead of thinking minus 1, 2, 3, minus 4, think of minus 1 plus 2x, etc. Okay, so we know this. And so a cyclic shift is, of course, a multiplication by x in that ring. All right, so these are cyclic lattices. We've seen them. Why? Why, as cryptographers, do we care about them? So, we have lattices. We have lots of theorems about lattices. But intuitively, it's not so efficient to use lattices. I'll give examples later. So one thing that cyclic lattices give us that can give us that general lattices cannot is that it is possible to represent cyclic lattices by just one vector, by just one polynomial. So obviously not all cyclic lattices can be represented by one polynomial, but some can be. Okay, so that's something that just cannot happen for a rank n lattice if it's doesn't have this symmetric structure. Then, of course, there's lots of ways to define things that have succinct representations. But the nice thing about cyclic lattices is that they have some algebraic structure. And algebraic structure is useful for constructing things. If we're going to do public key cryptography, you don't just want to do random, you can't have random things with no algebraic structure. You want some algebraic structure. And what this structure actually does is allows for fast arithmetic. So not only is it a nice representation, but actually multiplying things can be done faster. And this structure makes proofs possible. And we want proofs. So, there's Entro crypto system, which kind of use these. And, so for historical reasons, x to the n minus 1 is a nice ring to, sort of a popular ring to use. And then, I guess inspired by Entro, at least that's what Daniele says. So Daniele constructed one-way functions based on worst-case hardness of SVP in ideal lattices, in cyclic lattices. It should be cyclic. Okay, so this was in 2002. So in 2002, it was shown that there is you can build a one-way function, that if you can break this one-way function, you can find short vectors in cyclic lattices. Okay, so this kind of showed that, you can actually do something quite interesting based on cyclic lattices with a formal proof of security. So this is what I mean by makes proofs possible. Okay, so great that we have this result by Daniele. So the question is, is this a hard problem in cyclic lattices? So we believe that in general lattices, the shortest vector problem, and when I write SVP sort of sub-poly n, I mean approximating SVP to within a polynomial factor, maybe not finding the shortest vector, but maybe finding an approximation of by a factor of n or n squared of the shortest vector. Doesn't matter. But is it hard for cyclic lattices? So the short answer is we don't know, but we conjecture it is. So I'm smiling because I've given this talk a lot, but I think it's the first time that Daniele was in the room when I get. Yeah, you've never seen this. Yeah. So no, I'm not worried. But there's this slide here, and I always tell the story behind the slide, and people maybe don't think that it's true, but Daniele can probably confirm it. So what's wrong with the following argument that SVP sub n is easy? Yeah. So the story is that so I was just beginning my PhD, so Daniele was my advisor, and then he told me about cyclic lattices, and the next day I kind of run in and say, well, I'm done. I've solved it, and it's easy. So yeah, okay. When I show you the mistake, it'll be like no, but yeah, it's true. Okay, so here's my algorithm, but it's instructive, the mistake. So you have your cyclic lattice, and it's the shortest vector, and there is some shortest vector in O, right? We don't know what it is, but it's there, right? And let's say it's 1, 2, 3, 4, whatever, I don't care. Well, you know that all of its rotations are also in the lattice. Well, therefore the sum is also in the lattice. And the great thing is that all of these elements are going to be the same. It's a cyclic rotation. Okay? So the length of this one is at most n times the shortest vector. So that's it. And I thought, okay, wow.
But you also have to say how to find it, but then you
okay, yeah. Okay, yeah. I thought, okay, well, but then of course, yeah, it was very clever. So I realized this is a one-dimensional lattice, right? So all you have to do is construct a one-dimensional lattice, by intersecting your lattice with 1. Okay, that's easy. And, just search through all the possible things, or just run LLL on a one-dimensional lattice. That's fast.
LLL on a one-dimensional lattice?
Look, I was a first-year student. Okay, so.
I was very happy.
And, okay, so that's it. So that you have your length. So you can solve SVP within a factor of n. I mean, I felt a little sad for Daniele, having this paper that proved one-way functions based on cyclic lattices. But, okay. So obviously it's a mistake. There's a mistake somewhere.
Yeah.
I'm sorry? What?
1, 2, 3 minus 6.
1, 2, okay, yeah. So if this were 1, 2, 3 minus 6. Okay, good. So it's possible that, okay, sure, minus 1, 2, 3, minus 4, hopefully it's okay, that the sum of all the coefficients is going to be 0. So it's extremely disappointing.
And if it's not 0, isn't it still hard to find something where the sum of the coefficients is what it should be?
No, right? It's the shortest vector on this one-dimensional line, right?
Oh, okay, sure.
Yeah. So they're all the same.
Yeah.
Yeah.
That's not.
Yeah, that's easy. Okay, so that wasn't the problem. The problem was this, right? Okay, so what it intrinsically, what it really means, this, the fact that these are the lattices in which you cannot find the shortest vector, is that the hard instances of cyclic lattices are kind of restricted, right? And they are restricted to lattices that lie on this plane perpendicular to the 1 vector, right? So this is where the hard instances are. Okay? So in algebraic language, if we have our zx mod x to the n minus 1, then we're really wasting space in some sense by considering x to the n minus 1. Because the hard plane is actually, or the hard ring is actually zx mod x to the n minus 1 divided by x minus 1.
I guess another way to look at this is that up to, I guess, index n, this lattice is just a product of a one-dimensional lattice and an n minus one-dimensional lattice.
Sure, sure. And you don't want,
And finding the
Yeah.
short vector in the one-dimensional lattice
is quite easy. Sure, right. And but, you know, it's not just the product of any two, right? It's the fact that there are short vectors in the lattice can kind of be projected onto this one-dimensional lattice, right? This one-dimensional lattice actually has some short vectors, right? It's not just an arbitrary one-dimensional, because you know.
Well, I mean, up to index n, it's a product
Okay,
of
okay.
two lattices.
Okay, sure, sure. Yeah. But anyway, so in some sense, it doesn't even make sense to look at this x to the n minus 1. And honestly, after, personally, I don't see the point anymore of looking at zx mod x to the n minus 1. This is kind of, yeah.
Oh, we did it because it was so much fun.
Yeah.
And it made the computation so easy to put on a little 8-bit processor. It was entirely for fun reasons.
Right, okay, but as cryptographers, we're not supposed to have fun. So, you know, okay. No, but I'll show you that there are other polynomials that are equally fun, so it's okay. So first of all, so if you want to use x, so there's this one, right? But, you know, what if this guy factors more, right? So there's nothing special about x minus 1. I mean, it's a little bit special, but it could factor a little more into smaller degree polynomials, so that's bad. So what we kind of want to do is define ideal lattices as kind of sort of generalize these, you know, move away from cyclic lattices. There's nothing special with x to the n minus 1. Move for general f. Okay, so ideal lattices. And then we can actually prove some things when we look at SVP for general f, and actually build things based on the hardness of problems for zx mod f. Okay, and sort of we get these properties, the three properties that we want f to have. We didn't just say, we think they should have these properties. It actually, they kind of came out of proofs. We wanted to build something based on the hardness of this, and the proofs told us that it should have these properties. Right, so the first property is that said that f should be monic. Okay, you know, it's fine. It should be irreducible over z. So that kind of is kind of intuitive from, kind of rules out the previous attack against x to the n minus 1, right? And this third property is that you want to define some norm function on your vectors, right? And you want that the norm of the product to be not much bigger than the product of the norms. Okay, so when you reduce things mod f, so when you multiply two polynomials and reduce mod f, you actually can grow the norm by a lot, depending on how you define the norm. So what is the most obvious definition of norm? Well, look at the coefficients, right? The coefficients, that's the norm. Okay? So if you do that, then you have to be careful with which f you work. Another sort of natural thing is to look at the canonical embedding of each polynomial. So if you work in, for example, if you consider qx mod f as your number field, you have a canonical embedding, and you can define the norm as the L2 norm of the canonical embeddings, right? Actually, then you'll have gh mod f is actually equal to norm. The norm of the product will be equal to the product of the norms. Okay, because the things are component-wise. Multiplication. N is the, it's the degree of f.
It will be at most not equal then.
I don't understand why that is equal.
The problem is
Yeah,
that
yeah.
the norm is not
Yeah, it'll be at
actually
most.
a norm in the standard sense, and it doesn't satisfy the triangle inequality.
For addition?
Yeah.
So,
Why?
but I mean, for your canonical embedding, you don't have equality.
No, it's not equality.
Oh,
But it's a inequality, so less than or equal.
Because like in Z
meant
root
without
2,
the
there are
power.
units
Yeah,
that
without
have
the power.
norm 1, but they're written as like some giant multiple of 1 plus some giant multiple of the square root of 2.
But why is it doesn't not satisfy the triangle inequality? When you add two polynomials
You
together?
add two things. I mean,
Yeah.
think about the elements of the space. You can have units that are sums of things that aren't units.
Yeah.
So-
No, but I'm talking about not the multiplicative, not the field norm. I'm talking about the L2 norm. You do the embeddings, and then you look at the embeddings, and then you just do the L2 norm of the.
But that's not multiplicative.
No, right.
No, wait.
But there's the inequality.
Yeah.
Yeah, there's an inequality.
Yeah, there's an inequality. No, sure. But the embeddings are multiplicative, right? So,
You add them up.
sure. Yeah, fine. Okay. Yeah.
But if you're saying poly of n, does that mean you're considering a family of f's indexed by n?
No. I'm just saying for any f, right? You give me an f, and I will tell you, for this f, it's going to be less than n cubed times. Sure.
There's a constant depending on f.
So you give me an f, right? So it's x to the 100 plus x to the 99 plus 1. I tell you, okay, well, this is going to be less than 100 cubed times.
So the polynomial depends on f?
The
But in
polynomial?
fact, it's not even guaranteed to be a polynomial. It's
Yeah,
just a constant
we want
that
this.
depends on f, and for every n, you have a different constant. And you want it to be at most a polynomial. And for the special case of in the cyclotomic case, you can put.
It's not just the cyclotomic
no,
case.
cyclotomic, sorry.
For-
With the
depends on the
canonical
definition of the
index,
norm,
you
yeah.
can put one.
Well, the question only makes sense when you vary f. If f is fixed, it's a constant.
That's what I'm saying.
Yeah, sure. Yeah, okay.
Implicitly, okay.
But
Sure,
the
it's
dependency of the, if you have a family of f.
Yeah. Let's think of a family of f. Okay.
So how is the degree of the polynomial related to f?
What?
How is the degree of this polynomial that you get related to f?
Degree of the polynomial?
Well, you're saying
It-
that
Okay, so let's pretend, let me give you a family of f, okay? Let's say f is all the cyclotomic polynomials.
okay.
Okay, then this poly n, I mean, forget that it's not going to be poly n, and the norm is going to be the embedding, not the embedding, is the coefficient norm, right? Then there's a theorem of Erdős or whatever that this is n to the log n. Okay? So that's just one example. All right? So if I'm going to consider all the cyclotomic polynomials and the norm is a coefficient norm, this is going to be, and there's a proof that this is less than n to the log n. If this is going to be a family of just certain cyclotomic polynomials, let's say just of the form x to the n plus 1, then this is going to be n.
And is a power of
Maybe square root. For n power 2, square root of n. Yeah.
Why are we worried about this constant? Because, I mean, this equation is not homogeneous in the norm. I mean, if you multiply the norm by some large constant, then it changes the constants in that inequality.
What?
Like, if you just take your norm and you multiply it by 1,000,000, then the same inequality holds with 1/1,000,000 on the right-hand side.
What? So
Well,
I'm not.
because the right-hand side of that equation has 2 copies of the norm showing up, and the left-hand side has only 1. So if you scale the norm of everything by the same constant, you're making the right-hand side bigger by that constant square. Yeah. So, I mean, if you actually care about the constant there, then
No,
you
okay.
really need to care about something else about the
No,
norm.
yeah. Okay. I think we're. No, but look, hold on. Look, we want to have a bound. We're not trying to minimize, we're not trying to find a norm that minimizes this constant, right?
Okay, we want there to be a constant.
Because at some point we're going to get, through our proofs, we're going to get that if you could break some problem, then you're going to be able to find short vectors with respect to this, whatever norm you define. Well, it's not for any norm. I mean, of course, in these ideal labs. So if you define your norm in maybe the very silly way, then you may get a trivial sort of reduction, right? So look, let's not get bogged down in the math. Let's just say, I mean, look, I only know 2 types of norms, right? There's the coefficient norm, and then there's the canonical embedding norm. So let's just consider those 2. We're not going to want to consider anything else. I mean, those are just,
So you're taking this
Yeah.
with respect to which one of the two?
In what I'm going to, so if we consider x to the n plus 1, those polynomials, then it doesn't matter. Because they're just 90-degree rotations and scalings, yeah? If we take cyclotomics, then sort of the right thing to do is do the canonical embedding, okay? It's just cleaner, all right? Okay, so, all right, next time this is not going to be on the slides. Okay, so here's a conjecture. Well, here's an open problem. I think that for all f that satisfy the above three properties, you know, I mean, don't make up a definition of a norm. Well, maybe if you make up some definition of a norm, that's weird. That satisfy the above three properties, solving SVP poly n for ideals in Zx mod f takes time 2 to the n. So can you find an, I mean, choose your, you know, take a canonical norm or the coefficient norm, okay? Can you actually find some f that satisfies these three properties, but SVP in those ideals is not hard? I mean, we spent some time on this, but I have no idea how to approach this, right? So I think, you know, this is an interesting open problem. Okay, so okay.
Families of f?
Yeah, find a family of f's. Right? What? Yeah, for all families of, sure.
Not necessarily for all n, it could be, but for infinitely many n.
Well, no, but in fact, hold on. But what if you can just find one f, right?
What does 2 to the n mean?
Yeah, okay.
F, none of that is,
Yeah, one. Okay, fine. A family of f in a certain of a certain form. Sure. Then sure. The n.
so
Okay.
you need to specify the way the family grows.
Yeah.
As n grows. It makes sense
Right.
in theory.
But you know, okay, but sure. But even if you can do something, you know, not super precise, but just it'd be interesting. You know, you take an f that has dimension of, you know, degree 1,000, right? And all of a sudden you can find you can solve SVP in constant, you know, really fast.
Wow.
That would be pretty interesting.
Probably generate f together with an SVP solution.
No, but it's for all ideals, right? F just defines the ring, right? Right, so, okay, sure, but this could be another thing. Can you pre-process the ring somehow to help you solve? This is another open problem that I think is interesting, right? That would also be quite cool if you could pre-process the ring to solve SVP in all ideals. Yeah.
So by the way, the third condition is only needed for crypto functionality, or does it influence your conjecture in any way? It doesn't influence the conjecture.
Yeah, okay, sure. Maybe another open problem is, let's say this third property, good, is not satisfied. Can you somehow, are those lattices easier somehow, right? Because this one really only comes from proofs. Okay, I don't know. These are kind of problems that I guess people haven't either considered but failed or haven't considered. Okay, so some good f to use are, for example, this kind, this x to the n minus 1 divided by x minus 1 when n is prime, or you know, f equals x to the n plus 1 where n is a power of 2, which I claim is just as fun as x to the n minus 1. Actually more fun because it has some interesting structure. Okay, so when n is a power of 2, this is irreducible. And that's it. That's the only time it is. All right, so what we have done since that time is really mostly consider this, okay, for cryptography. So, and in this talk, I'm really going to concentrate just on this, except that in the very last slide, I will generalize a little bit. Okay? So now just a brief recap. X to the n plus 1 ideal lattices are ideals in Zx mod x to the n plus 1. They have the same three properties, right? But if you now think about shifts, you know, they're not shifts anymore, but they're shifts with negation. So negative 1, 2, 3 minus 4 is in the lattice, implies that 4 minus 1, 2, 3 is in the lattice, and so on. So because x to the n is minus 1. Okay, so these are the lattices I'm going to consider from now on. So when I say ideal lattices, I'm going to mean that until the very last slide of the talk. All right? If you want to generalize, you know, okay. So Daniele had this graph of lattice problems, and I have a table. I guess his graph was nicer, so I was going to draw this. So here's gap SVP. There was BDD. What else was there on top?
Gap SIVP.
No, it's not necessary. Then there's SIVP, and then there was SVP here. Okay, and ignore USVP, unique SVP, forget it. Okay, so if you remember, gap SVP was given a lattice, find the short vector, SIVP given a lattice find all the n short vectors, sort of linearly independent ones. Gap SVP was the decision problem SVP. And BDD was you're given a lattice point really close to the a point close to the lattice, find the nearest lattice point. Okay. So for general lattices, these problems SVP, SIVP, BDD, Gap SVP are NP hard in the exact versions. For ideal lattices, we know nothing. Okay. The poly-n approximate versions of general lattices, we know nothing. There's no, I mean, we believe they're not NP hard, otherwise some bad things in complexity will happen. But we know that, for example, we know some properties, some equalities. So for example, for general lattices, we know that Gap SVP and BDD are the same. So this was Daniele's thing. Okay. Now, the weird thing is, I guess it's not weird once you see the proof, it's obvious, is that for ideal lattices, Gap SVP is actually easy. So this is a bit scary. You know, you have this decision problem that is on which crypto is based for general lattices, but it's easy for ideal lattices. Okay, I'll show you the proof. The proof is easy too. Okay, and so for general lattices, you have these equalities between Gap SVP and BDD, right? You had the equality for general lattices, but for ideal lattices, that would be bad because actually our problems are based on BDD, but Gap SVP is easy. So the proof actually doesn't work. So some different things are going on. Okay? And this is why I think it's quite important to have sort of a different set of proofs for your ideal lattices. You can't just say, well, you know, we have regular lattices, well, let's add some symmetric structure, and you know, the same things will be okay. They may or may not be, but it's a bit scary, I think. Especially.
Sorry, Daniel was using the x to the n minus 1 ideal lattices. You're using the x to the n plus 1, and it's the same.
Daniele was using.
The minus assumptions are same if you use xn plus 1 and x to the n minus 1.
Are the same.
Well,
No, Daniele was using general lattices. There's no x to the n.
Not in my talk. You meant when you.
You meant in his talk, or?
No, when you were talking about me. That's what you meant.
No.
But I never mentioned x to the n.
Okay.
So did I?
Okay, now I'm sorry.
Okay. Okay, yeah. All right. So, okay. So the point is that you know, proofs need to be made. All right. So let's sort of prove some obvious things, that SVP actually equals to SIVP in ideal lattices. Okay. So this is, and it doesn't matter which embedding you take. So the nice thing for x to the n plus 1 is that the coefficient norm and the canonical embedding norm are actually sort of the same up to a scaling. Okay, because when you do the embeddings in, you know, so that the ring of integers of zx mod x to the n plus 1 is really the ring z adjoint zeta of 2 to the 2n. Yeah.
2n.
Oh, sorry. Yeah, 2n. Yeah. Okay. So, and this is sort of pretty unique among cyclotomics. All right, so SVP equals SIVP is pretty easy, actually. So you have some vector, polynomial, right? F is monic. So you have v, vx, vx squared, vx n minus 1 are all linearly independent. So if v is the shortest vector, then all its rotations are actually linearly independent. Sort of, that's a fact. Right, so once you have one short vector, you have n linearly independent short vectors. Okay, so, and they're all the same length, no matter which embedding you use, canonical embedding or the coefficient embedding. So just for simplicity, I'm just going to use the coefficient embedding in the talk. Okay. All right. So now the sort of the scary one that so SVP, what we conjecture is hard, but the decision problem is actually easy to approximate to within a root factor of root n, and this is a one-page proof. One-line, two-line proof. So we're going to show that all you have to do to compute the approximation to lambda 1 is compute the determinant of L and take it to the power 1 over n. Okay, so I'm claiming that lambda 1 is between root n times the determinant and between the determinant to the 1 over n. Okay, so the proof of this is simple. To prove this part, you use Minkowski's theorem. Okay, that's it. To prove the second part, you use this fact. So you assume you have there is a shortest vector of L, that's V, and define a lattice generated by V, a sublattice of L generated by V. Okay, so it's a sublattice of L, so we have the determinant of L is at most the determinant of L prime, right? The determinant of sublattice is at least the determinant of the lattice, right? And determinant of L prime is less than or equal to the norm of V to the n, right? Because it's formed by V, Vx, Vx squared. All of them have norm V, so it's less than or equal to V to the n, and that's equal to lambda 1 of L to the n. That's it, okay? So gap SVP is easy, within a factor of root n. Okay. So search problem hard, we believe. Decision problems easy. All right. So now, what is the point of ideal lattices? What is the point of doing things? So if you remember in Daniele's talk, he talked about Lattice function. So I don't know if he didn't use the word SIS, but Lattice called a small independent solutions problem, right? And the problem was basically given a matrix A, find the short vector Z so that AZ equals 0, okay? And sort of the one-way function implied by this hard problem is given a vector A, pick a random short Z, multiply A times Z. And the problem is, can you recover some Z? Okay? All right, so what's the sort, even this is the simplest thing, one-way functions, but it's already quite inefficient because to represent this A, at least even to represent the function, requires n times m sort of numbers, right? And n is about 200, m is about 500. So now you have whatever 200 times 500 is, which is quite big. Okay? This is too much, and this is just for one-way functions, right? We want to do more things. So that's not good. But the more efficient idea, at least using something about ideal lattice, at least the symmetric structure, is to say, well, what if we define A like this? We define it, you pick the first column, and then the next columns are going to be these negative rotations. And then, okay, well, we can't do a negative rotation of this one. We'll get the same thing. So we pick another column and do this, and then do this multiplication, right? Now, if this function is sort of one way, then A only requires order m storage. And so you saved a factor of n. And also, A times Z can be computed much faster. Okay? Oh. Interesting. No, it's okay. All this says is, I'm guessing, well, it said that matrix, A times Z, can be thought of as a product of two polynomials. So you can just look at, there's A times this part, plus this part of A times this. You can think of it as, this is a polynomial 4 plus 7x plus 2x squared plus x cubed times 1 plus x cubed, right, plus the other part. It's just this matrix vector product can be thought of as a product, a sum of products of two polynomials. I hope this should be pretty clear. I hope it doesn't do this for other things. Okay. All right. So for this, we defined the ring version of Lattice problem. And the thing is, and the problem is sort of naturally defined as follows: given k random polynomials a1, ak in zpx mod xn plus 1, find small polynomials so that a1, z1 plus that plus ak, zk equals 0. Okay? So Lattice problem was given a, find a small z so that az equals 0. We said given a few polynomials, find a sum of the products that equals 0. Okay? And what we were able to prove that if you can solve this ring cis problem for random polynomials A, you can approximate the shortest vector problem, actually, the shortest vector problem, find the approximate shortest vector in any x to the n plus 1 ideal lattice. Okay? So this is where, this one? You want me to talk or just show it? Okay, so we were only able to do this proof because we sort of used this polynomial x to the n plus 1 that satisfied those three properties that I wanted, right? So it's not that we picked those three properties because we think these are cool properties. No, it was really dictated by the proof. We could not do the proof with x to the n minus 1 because actually it would be false. With x to the n minus 1, we could only get one-way functions. Well, Daniele could only get one-way functions, right? If you want to do more things like collision-resistant functions, digital signatures, ID schemes, you need those three properties.
So when you say any x to the n plus 1,
any
some related one to the one for the ring sys that's being used?
I'm sorry?
So let's say you had the ring sys for some n, and you solving SVP in any n or some related?
No, it has to be the same. I mean, the n was the degree of those polynomials, random polynomials AIs. Those were the n.
And it has to be cyclotomic as well? Or
what it has to be cyclotomic?
X to the n plus 1 has to be a cyclotomic polynomial?
Well, x to the n plus 1 is a cyclotomic.
Not for every n, right?
No, it has to be a power. Right, it has to satisfy those three properties, right? One of the properties was irreducible. So once it's irreducible,
X to the 5 plus 1, it's not cyclic, is it?
it's not irreducible. Yeah, it has to be irreducible, right? Right, unless 5 is, yeah. Then it's cyclotomic as well. What?
So you're restricting to n powers?
We're restricting to irreducible polynomials. So yeah, exactly, sure. But it's not that we care about powers of 2, right? I mean, because powers of 2 is kind of a nice little coincidence. In crypto, in sort of computer science, we like powers of 2, and so that's not why we use powers of 2. Powers of 2 came because these are the irreducible ones. Okay.
Sorry, I'm going to slow you down a little. Just a few connecting verbs somewhere. So the ring-LWE problem is the one you wrote before?
The slide that I went back to, yeah.
You're saying that if that's difficult, then approximate SVP is also difficult?
I'm saying that if that's easy, then approximate SVP is easy.
Oh, the other way.
Yeah. All right. So, but notice that with the SIS problem, we can only get these things, and something important is missing. Actually, what is encryption. And for that, we can't get, and this was kind of Daniele, remember if he kind of drew this thing. This was public key crypto. This was secret key crypto. No, the other way, sorry. Public key, secret key. Yeah, so with this, but things are now a little bit different because SVP equals SIVP. So this is whole thing. So we can get secret key crypto based on SVP in ideal lattices. But what about public key crypto, right?
Wait, so can you repeat that sentence? That you said if ring SIS is easy, then approximate SVP is easy. But can you put in the words worst case and average case in that sentence?
So if average case ring sys is easy, then worst case approximate SVP is easy. Okay. All right. But so a lot was missing, and so we needed an LWE equivalent analogy for rings. And so here's the LWE problem, sort of in pictures, what Shai did in letters. So you have this matrix, you multiply it by some secret, you add some noise, and you get these two outputs. Okay? And now the question is, well, the problem is, can you find this S? So you have A times S plus E equals B. Can you find S? Okay? And E is small. All right, so it's a system of linear equations perturbed by a little noise. So this is LWE. Well, still, same inefficiency problem, right? Big matrix, hard to represent. Same idea. Use the same efficient idea. Put in, make this multiplication a multiplication of polynomials. Okay? All right, is this secure? Can we prove this? And so, yes, it does turn out to be secure. And there's a quantum reduction from average case learning with errors to worst case approximate SVP. All right, and from this you get sort of everything you want. Okay, so here's the sort of the formal definition of Ring-LWE. You're given a ring, there's a ring R, right, xn plus 1. You're given random A1, then A1 times S plus E1, random A2, A2 times S plus E2, random AK, AK times S plus EK. So the red ones are secret. S is random in R, EI are small. And the distribution, we'll talk about it later. I'll just tell you that it's symmetric around 0. So each coefficient of E is symmetric around 0. These are all polynomials. Okay? The goal is to find S. Now, in cryptography, we don't really like working with search problems. You can't get, it's not easy to get reductions. You know, if you can break this encryption scheme, then you can find S. That doesn't really work that way. Most definitions in cryptography require decision problems. It's like pseudo-randomness. Is this like this? Is this sort of different than this or not? And to break something, all you have to do is decide whether or not these two things come from the same distribution. So it's much easier to work with decision problems. And this is what we want to prove is hard. But you know, it's scary because the decision problem of decision version of SVP was easy. So maybe the decision version of LWE is easy as well. So here you're given a ring R. And you have A1, B1, A2, B2 up to AK, BK. And the question is, does there exist an S and a small errors so that HBI is AIS plus EI? Or are all the BI just uniform and random in R? So that's the question for decision LWE. And this, I think, is sort of now one of the central problems in lattice-based cryptography. Right? Upon this problem, almost everything is based. Efficient. Okay, so this is decision Ring-LWE. And the question is, so this is sort of the, I don't know, the colorful version of the problem, right? You have two possible worlds, world 1 and world 2. World 2 is where everything is random, the AIs are random. World 1 is where the AIs are random and the BIs are AI times S plus EI. And you have some, you want to build this oracle that takes either, you know, has access to either this world or this world, and it has to decide which world is he in. Okay? This is decision Ring-LWE. And what we want to show is that, so what we sort of showed in the connection between Ring-LWE and the lattice problems is it was in two steps. In the first step, which was kind of similar to the LWE step, is to show that the search version is hard. We show that the search problem, if you can break the search version of Ring-LWE, then you can quantumly solve all sort of ideal lattice problems, SVP and ideal lattices. And that was very similar to Regev's 05 paper. The decision version is actually quite different, a bit different. Okay, and this is what I'm going to talk about for the rest of the talk. Okay, so what we want to show is the following. We have an oracle that actually solves the search Ring-LWE problem. And we have an oracle that solves the decision Ring-LWE problem. And we want to use this oracle to solve the search Ring-LWE problem. Okay, so we want to show that decision is no harder than search, is no easier than search. Okay, so for LWE, this is actually very easy. And I'm going to show why. For Ring-LWE, it's not as easy and introduces some restrictions. And this is where we get cyclotomics. OK, so let me do the decision LWE problem for regular lattices, no rings. Here's world 1. Here's world 2. And you have to decide between the two worlds. In world 1, this is random, so you have A times S plus E. World 2 is you have A and B. OK? And you want to construct an oracle that takes A and B and says, I'm in world 1 or world 2. This is the decision LWE problem. And you can show that if you can solve decision LWE, you can solve search LWE. And the proof is actually very simple. It's based on a proof from the 80s, maybe even earlier. I don't know. So the idea is to use the decision oracle to figure out the coefficients of the secret S 1 bit at a time. So here's the idea. let's say we make a guess for the first coefficient of S. And we repeat the following. So here's our S. We don't know what this S is, right? We get this and this, but we make a guess for the first coefficient of S. We receive the LWE pair A and B, right? And we let G be our guess for this. So correct guess would be 8. And we're working mod 17, okay? So pick a random R in Z17, and then send this sample to the decision oracle. Add R to 2, to the first position, and add R times G to B. Notice that the first position of the secret is only sort of touched by the first position of A. So if we added R, how should this modify the B? The R just gets multiplied by 8. If our guess was really 8, then what we sent here is actually a perfectly valid sample. Okay? So if G is correct, then we're sending a distribution from world 1, the LWE world.
So you get to choose, I mean, is a decision involved that you get to choose something about the pair?
So look, I have access to a decision oracle, right? And I want to, but I want to solve search version, right? So in the search version of the problem, I get A's and B's, right? I get random A's and some B, such that B equals AS plus E in the search version, right? And I have to find S. So to the decision oracle, I give him instances that are either completely random or actual, valid instances. So I could just forward him the instances that I get, but then I know his answer. His answer will be, these are valid instances. So I want to be able to modify things sometimes so that sometimes they're valid and sometimes they're completely random. Yeah? So, I mean, I can always just give him valid instances. That's easy. I can also always just give him random instances. Okay? But I want to do something that will somehow, depend on, the correct answer. And, okay. So if the guess is correct, then we're sending him valid instances. We actually haven't changed anything. If the guess is wrong, you have to do, 2 lines of work, probabilities, to figure out that actually this is going to be completely random.
Yeah, and so you assume that the error is so small that it doesn't influence the work, right? Because
The error has nothing to do.
You will get the same error as the last time, or
maybe
even
you will get the same error. No, it's the same exact error.
Well, the error in the first line is 1, and the error in the second line is actually multiplied.
No.
Oh, it's not.
No.
Oh, sorry.
No, but good. Okay. So we will find the right G in order of p time. Okay. So we guessed the G. If he said, okay. So we'll find the right G in order of p time. If p is small, we're good. And p is going to be small usually. Okay.
How does this work if the decision oracle is only right 60% of the time?
Because, so I was going to get to it at the very end, but the idea is that this problem is random self-reducible. So if I have an instance for, if I want to solve the problem for worst case, if I need to solve the problem for worst case S, I can re-randomize it for a random S. So every